Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Ashraf and today I will explain on Lab 2 which covers chapter Fluid Dynamics and I will explain on Bernoulli equation. Okay, for the theory part, law of conservation of energy is one of the main factors behind the derivation of the Bernoulli's principle. Bernoulli's principle states that sum of all energies, which includes kinetic energy, fluid pressure, dynamic head, and potential energy, should remain constant at all flow points in a steady flow. So, if one type of energy increases, the other type of energy will decrease to ensure that the initial sum of energy is same as final sum of energy. The equations are P plus half rho v square plus gamma z equal to C, and P over gamma plus v square over 2g plus z equal to C, where P is pressure, V is fluid velocity, Z is height, G is acceleration due to gravity, rho is fluid velocity, and gamma is specific gravity. Okay, let's move on to the introduction. According to the Bernoulli's principle, if area available for the fluid to flow decrease, which means that the smaller the area, the velocity of the flowing fluid will increase, and at the same time, the pressure of the fluid will and its potential energy will decrease. So in this experiment, we will use a Bernoulli to measure the fluid flow through a pipeline. It has a converging and a diverging portion used to increase and decrease the velocity of the fluid. Next, it has a throat that will produce a low pressure point so that the pressure can be compared to either the upstream pressure or downstream pressure. Okay, there are two objectives. The first one is to demonstrate the validity of Bernoulli's principle, which is as velocity increase, pressure will decrease. And the second one is to determine the relationship between fluid velocity and pressure. Alright, figure 1 here shows a diagram of 100 meter. As you can see, there is a converging portion, a throat, and a diverging portion, and there is a difference between H1 and H2 due to the velocity of fluid. Okay, figure 2 here shows the experiment setup. It is quite simple because we only use centimeter. The parts are micrometer, test section, water inlet, unions, air plate screw, discharge valve, grand nuts, hypodermic probe, and adjustable plate used to balance the meter. Okay, after the experiment had been conducted, these are the results obtained and I have sorted out in the table. We use a different cross-section area, which is section A has a diameter of 26 mm, B is 21.6 mm, C is 16 mm, D is 20 mm, E is 22 mm, and F is the same as A, which is 26 mm. Okay, from the value of H1 and H2, we calculate the pressure using P is equal to rho GH. After we obtain P1 and P2, we can calculate the pressure difference to show that there is a pressure drop. Okay, V1 is calculated using the Bernoulli equation and V2 is calculated using the fluid flow rate or continuity equation. And the flow rate for this experiment is 3.22 times 10 to the power negative 4 meter cube per second. Here are the sample calculations, and this calculation will only refer to section A with a diameter of 56 mm. As you can see, all the formula and equations are used. Okay, so the experiment had demonstrated Bernoulli's principle. From the results obtained, we can see that as the area of fluid flow becomes smaller, the velocity of fluid is decreased. This will also result in a drop in pressure, and the biggest pressure drop is shown in section C, where the diameter is smallest at 16 mm. Two different equations were used to calculate the velocity of fluid, which are Vv is equal to square root 2g h1 minus h2, which is from the Bernoulli equation, and Vf is equal to Q over A, which is taken from the volume flow rate or continuity equation. The pressure fluid of at a different cross-section of the ventrimeter calculated by using this formula, which is P is equal to rho GH. Okay, to conclude the experiment, the Bernoulli principle states that high fluid velocity will result in low pressure. So, from the volume flow rate equation, smaller area will also increase the velocity of fluid. Both equations shows the same increment and decrement pattern of velocity of fluid at different cross-section of the ventrimeter. This means that both equations can be used to determine the velocity of fluid flowing inside a pipe. So the Bernoulli principle is valid, and we know that from this experiment, the pressure is inversely proportional with velocity, and as the velocity increases, pressure will decrease. That's all from me. Thank you.